Good evening, all. We are now going to begin the last technical session of the ATAL Online FDP on quantum intelligence, integrating quantum technology with AI and ML. Now, speaker of this session is Mr. Shudhendu Bikash Mondol. Mr. Shudhendu Bikash Mondol is a highly qualified researcher working with TCT Crest as Senior Quantum Software Engineer. He did his BTech and MTech in Information Technology from University of Calcutta, specializing in quantum circuits and algorithms. His distinction as an IBM certified associate developer in QSKIT qualifies him to lead and significantly contribute to quantum computing aspects. Mr. Mondal possesses extensive hands-on experience in implementing complex computational model, quantum circuits, and algorithms. He also served as an assistant professor in Sister Nivedita University and Calcutta University as visiting faculty. May I request Mr. Mondal to start his session.
Thank you, madam. Am I audible? Hello. Hello. Am I audible?
Yes, sir. Yes.
Oh, okay. So first, thank you for this kind introduction. So I'm sharing my slides. First of all, good evening to all of you. Today I will discuss about our ongoing research topic. This is still we are doing research on this topic. This is quantum circuit synthesis of an approximate high-bit Kolmogorov-Arnold network. I will say why I'm saying this is approximate. And why it is hybrid Kolmogorov-Arnold network. Actually, throughout this talk, I will uh, explain how we can create a quantum circuits for these Kolmogorov-Arnold networks, and we will show some results, but still this result may not be a good results because still it is going on ongoing research. So I try to say that what is the capability of this model, and I try to make this presentation is as simple as so that we can understand as much as possible. And before going to the directly to this topic, I will briefly discuss about the basics of quantum machine learning. I know in this FDP session, Professor Omran Chakraborty also delivered this what is quantum machine learning, what are the different techniques, what are the use case also. So I will not go deeply in this topic. Just for recap purpose, I will give you some idea. And also, I know today's in the previous session, you will get in some idea about the noise, what are the different noise suppression techniques from the Ritojit and Amit's lecture. So I will not discuss this part also. Let's start. First of all, today's goal of this today's talk is to we just proposed a one quantum circuits, or rather, I think you have all of you are the familiar with some terminologies like answers or something. So uh, we can say this quantum answers. This one we have already created. For this Kolmogorov-Arnold networks. I will discuss this, and especially this design is for the Nix-Kera computing, not a fault-tolerant computing. And also, I try to show some results. These can work on synthetic data set or some real-world data set, but it's some toy models. but we have a future plan to do experiment with a real world model, a real world data set also. So I think all of you know these slides. What is the basics of quantum computing? Throughout these 6 days FDP, you have already learned what is superpositions, and these are the very basic quantum computing phenomenon, or you can say the properties. This one is the superposition. You have all know in classical computing, there is only data can stay either 0 or either 1. But in case of quantum computing, we can represent one data as a superposition of these two, 0 and 1. I know all details, you know all of these things. And another very good property is of quantum computing. This one is entanglement. This is nothing but a correlation between the two qubit system. Analogically, you can think that you have two gloves. One gloves in and you put in the one boxes, and another gloves you can put in another box, and the and one box you can send to the moon. Now, if you open your box and if you check this, okay, your gloves is left hand gloves, then automatically you can understand that moon's box contain the right hand gloves. This is the beauty of entanglement. After making this correlation, if you separate these two qubit from the any long distance, hypothetically, any long distance, practically it is still now possible to show the long distance entanglement. And there is a still challenging practically, but theoretically you can say if you separate these two things, then if you measure one, then you can get some idea about the state of this another qubit. Uh, these properties also help us lot for this quantum computing algorithms, defining the different quantum algorithms, and it can by using these two properties practically, this superposition or entanglement properties. By using these two, you can get an extra advantage which one you will not get in case of your classical computing. By with the help of these two properties, you can design a good quantum algorithm. uh, I think all of you know through the session there are so many quantum algorithms you will be familiar. Then another property is there is an interference. Here we will get also another type of interference. This is called destructive as well as constructive interference. These properties also help us to getting some quantum advantage to design a quantum algorithm. And another important thing is quantum measurement. See, in quantum computing, everything I told you that this superposition, entanglement, this is under in the probabilistic space. If you think about the, I think all of you know the Hilbert space concept throughout the session. So within this Hilbert space or in the probabilistic space, you can do this type of, you can get these properties. Uh, Maybe my this statement is not a fully physics angle correct statement, but for to understanding purpose, I can say some loose comment there. Suppose in quantum computing exists in probabilistic space, but from the human readability, we can't read this or we can't understand this probabilistic space. We know the deterministic outcome, so make as an outcome we need to measure the quantum state. And what is that meaning? Suppose I have a one box. Again, I'm giving the analytical example. I have a box. I put some ball within this box, and before putting that, I have a two balls like red ball and green ball, and I put some one of this ball to this box. And if I ask you when box is closed, if I ask you that what is the color of box, you can give the answer. You can give a good answer like that 50% chance of red ball or 50% chance of green ball. But this is not a human readability because it is in probabilistic space. Now, if I open this ball, I can check the color of this ball. Now, this is the classical state, and this is actually a measurement in quantum computing. Measurement means actually quantum state will collapse. So we can get the actual deterministic outcomes. So all of these properties we have required for design a quantum algorithm, because quantum algorithm can moves in the quantum space, but result should be comes into the classical world. That's why measurement is very important. So next, these things I think also details about this. This is the basic pipeline architecture of quantum computer. Within this block, you can see uh, this is the stack. This is the actually a full stack of our quantum computer. Uh, this one is our problem statement. So from this problem statement, we have to first constitute or design the algorithm. Since we need to formalize this, for example, this is the quantum algorithm. Like if you are already familiar with Gover's algorithm, you are familiar with Short's algorithm or HHL algorithm. So and for this particular problem statement, you have required one of these algorithm, or maybe two algorithms you have required. So you form your algorithm. Then you have to convert this algorithm to some programming language. In quantum computing world, there are so many programming language exist. Most popular programming language is Qiskit. I think Ritujit explained very well in the previous session. Qiskit is one of the programming language. Another programming language is called SART. So this is developed by Google. There are so many. So you have to first convert this your traditional algorithm to some programming language. Then comes into the role of transpiler. Actually, what is the need of this transpiler? Transpiler actually, see, in world of quantum computing, there are several kind of quantum computer exist, and their building technology also are different. One may be a superconductor based, one is iron based, and uh, another can be a photonics based. So they have a different technology, they have a different basis gate set. Uh, I'm not, this is suppose in a superconducting quantum computer there may be a basis gate set like SX gate, or some T gate, or your CX gate, or ECR gate. This can be a one kind of your basis gate set. This is called a Clifford plus T gate. And for the ion trap device, that is company name is IonQ or Continuum. They have a different basis gate sets. And for IonQ, there is GPI1, GPI2, and there is a entangled gate is like called RZZ gate, like this. Uh, what is that basis gate? Actually, this basis gate can be understandable by the lower level hardware or lower level quantum computer. In this corner there is I am putting some quantum gates. They are the mostly logical quantum gates. For building this programming language, we can use this logical quantum gate, but this logical quantum gate cannot be directly implementable in real hardware, because real hardware can understand some basis gates, and this is different for the different quantum hardware. So transpiler actually plays role here. Your programming language converted to a some basis quantum gate sets, or we can say your program can be written in terms of some basics gates which can be understandable by the your real hardware target quantum computer. And also there is another role of transpiler, because in quantum computer there is a qubit, and within this qubit there is a connectivity. In some quantum computer like IBM hardware, actually they have a topology like a heavy hexagonal topology. But in case of ion trap machine like IonQ, they have all-to-all connectivity. So we have to map our quantum circuit according to this topology. So transpiler also plays this role crucially. Another rules of transpiler has to find the best qubit, because we are not in a fault tolerant area. we are present in a niche scalar. So all qubits are not good. Good qubit means its fidelity, its decoherence time, its different characterizations are also there. So depending on this, we can find this one is good qubit or this one is bad qubit. Always for our problem statement, we try to find the best qubit. And this job has been done by this transpiler. Then after this transpilation, by using compiler, we need to convert our instruction set to a microarchitecture instruction that is called a pulse level programming, because any qubit can understand only the pulse. So we have to convert it to the pulse level structure. This is called this microarchitecture or analog instruction. Then it goes to the quantum processor. This is the basic pipeline architecture of our any quantum computer. This is very generalized stack I'm showing. So I think uh, this is already known by you, but still for a recap purpose, I just gave you this. Next, in quantum machine learning, in quantum machine learning, this part also very explained by the Professor Amlan Chakravarti in details. So I'll not go in details. Just for knowledge base, I'm explaining this. What is the quantum machine learning in this block? This is the very popular picture in left corner picture. Nowadays, if you hear any quantum machine learning lecture, everyone shows this left corner picture. Here, machine learning can be divided into four types of job. One is say that classical data with classical machine learning problem statement. Another part is classical data but quantum machine learning model. Another is quantum data and classical. We want to in classical classical computer. Another is quantum data and quantum computer. All of you know these part classical data and classical machine learning model are executed in a classical computer. Uh, and next, this classical data implemented by using quantum machine learning model in quantum computer. Today's talk, I will stick on these two part, this part, and basically classical data we have to encode in a quantum machine learning model, and we have to execute this is in a quantum computer. And this part is quantum data. What is what is quantum data? Actually, quantum data is if you have some quantum sensor source like a quantum magnetometer or some atom informator, and they didn't give outcome as a just voltage, but they give a outcome as a magnetic field, uh, uh, as well as also the gravity, as well as the time. Everything is punching with this. This is called quantum data. They will supply. So there are still there is a very few works done on this quantum data with classical machine learning model in classical computer. Actually, in this topic, so many physicists try to understand the different phase. After giving some quenching in this phase, they try to find the materials property by getting this quantum data. There are so many works is there, but there is a very few research work in quantum data with quantum machine learning model. See, still now quantum computer is not so powerful. So this is very difficult task to handling the quantum data. Still challenging for the classical data also in quantum machine learning. Uh, it's I can comment on this. Still, quantum machine learning is not can beat the classical machine learning model. I can't say like this. Still, it is a underperforming model and also still in a research model, not in the in ready-made application area is still not due to the your quantum computer is still now is not a so powerful and good machine is available in terms of qubit as well as in terms of fidelity or other characterization. So this quantum data and quantum machine learning, this part research is there is very few research exists. But as a quantum computer engineer or quantum computer researcher, they still focus on this research area we have a classical data. How can we encode this classical data into quantum computer, and what will be the different quantum machine learning model? And when we say the quantum machine learning, so automatically comes some algorithms name. You know the quantum phase estimation algorithm. There is this is obviously fault tolerant algorithm, quantum phase estimation. We can get an exponential speed up. Actually, in quantum phase estimation algorithm, we try to encode our very large matrix eigenvalue to this quantum phase and read out in different process. And there is a quantum amplitude estimation, quantum Fourier transform, as well as HHL algorithm. They have a lot of application in quantum machine learning, like for doing the PCA in classical machine learning. PCA is a very costly process, so you can reduce the cost, resource cost, as well as the time, reduce the time to computing by using the HHL algorithm. There are so many papers for say, and if you in the support vector machine work, there for cluster finding, uh, their Gover search algorithm also plays a very good role. It gives you the quadratic speed up than the any classical algorithm. But all of these are the fault tolerant algorithm. To implement this next era is very challenging, and probably I can comment it is impossible to implement the this fault tolerant algorithm in Niskera machine. For a few qubit, like 1 qubit or 2 qubit problem, it can be possible to implement, but there is no quantum advantage within this 1 or 2 qubit. So, tackling this quantum machine learning problem, there is some Niskera algorithm. This is called variational quantum algorithms, like quantum eigensolvers or quantum approximation optimization algorithm. They are the Niskera algorithm. They are the hybrid algorithm. Some hard part we can do in quantum computer, and some others part we also take the help of classical computer. And these quantum circuits all are PQC circuit, that means parametric quantum circuit. We optimize this parameter with the help of the some classical optimizer. So in next era, we will concentrate this kind of algorithm for doing machine learning. As our Kolmogorov-Arnold network is also a Niskera problem, so it is also a quantum classical hybrid network structure. I will explain in later. So for any kind of machine learning in quantum machine learning problem, there is this one is the most challenging part. How can we encode the classical data to a quantum computer? For our Kolmogorov-Arnold network, we have also required this because we are concentrating on classical data in quantum machine learning model. We want to implement a quantum hardware. So in this sense, obviously we have to input this classical data because some machine learning problem we have a features. This features data set is a classical data set. So we have to input this into the quantum machine. I know Professor Amlan Chakra also explained all of this basis encoding amplitude in detail, but just for the review purpose, I'm telling this. There are three kind of encoding technique exists. One is called a basis encoding technique. In this basis encoding technique, our target is to the classical data we want to encode in a basis vector like 0, 1 basis state, quantum state. We want to encode this. So what is the step? Here we have to convert the classical data to the binary decimal to the binary forms. And these binary forms, after represent, we need to some technique for positive and negative data. We use some another extra bit. So after that, we can make a actual state by flipping some not operation or Pauli X operators. We can prepare this state. This is a very easy and straightforward technique, but there is a problem. One thing, it's required huge number of qubit. Suppose for this real data, if you want to convert it to a binary, if you need a precision, if you need a more precision, then you have to represent by more number of bits. This one is first challenge. And suppose there is a, I have taking only three feature statuses, but if feature set is huge, if there is a features vector contain more than 1,000 features. So to implement this to a basis to encode this data into the by using basis encoding technique, we have required huge number of qubit. You can with a good precision. So now in real world, there is a publicly available quantum computer is mostly 157 qubit from the IBM's quantum computer. So so within this few qubits, to encode the basis encode by using basis encode classical data encoding is very challenging, or rather it is very impossible. Next encoding technique is amplitude encoding. In case of amplitude encoding, first we have some feature set. We have to convert this feature set to a quantum state like a size this psi equal to this. For doing this, we need to normalize this data, because in quantum computer any state we can say alpha 0 plus beta 1. So there is alpha and beta should be normalized, and this toward the complex number, and mod of alpha square plus mod of beta square should be 1. This is for the normalization condition. So we have required this data to make a normalization, uh, and then also we have required to data set represent with a log of 2x data logarithm constant, because suppose in quantum computer for 4 data encoding, we have required 2 qubit, because 2 over 2 is 4. Similarly, if you have a n number of features to encode this, you have required a log of n number of qubits. So that's why if you have a 3 number of features, so another to make it a 4, we need to embed another data with a 0, which has no contribution. That's why we take this 0 here. So by using amplitude encoding, we get one advantage than the basis encoding. What is the advantage? We can represent classical data with a fewer number of qubits, and it's required in a logarithmic scale number of qubit to represent the classical data. For example, if you have a n number of features in your data set, then you can to encode this data into a quantum computer by using amplitude encoding, you have required a log of n number of qubits. So in terms of qubit requirements, it's required less number of qubits. But there is a one challenge to after this normalization to encode, because encoding the equal superposition is very simple. From if we want to make a equal superposition of 4 state, then it is very easy. We have required 2 qubit and we put the Hadamard gate there. So equal superposition is very easily. Here, this psi state, you can see this psi is equal to 0.07800 or something. This is one of the superposition state, but this is not an equal superposition state. So state preparation is also another challenging area or challenging research area still now exists in quantum computing. So we can mathematically prepare this state after doing some normalization and everything we can do. Yeah. Okay. So making this mathematically, this superposition state is fine. But to make the quantum circuit corresponding this unequal superposition state is very challenging, and it has required huge number of 2 qubit gate and huge number of 1 qubit gate. So circuit depth will be very high for this amplitude encoding. So sometimes if you, I can say for example case, if you have a more than 50 features or say 64 features, so you have required 8 qubit. So in terms of qubit, it's very handy. But these features encoding, you have required at least 902 qubit gates. This is uh, very challenging to implement in nowadays least quantum computer. So in terms, this is the major disadvantage of amplitude encoding. Now, another encoding case is angle encoding. This is also a simple, and and this is possible to implement because here task is very simple. We have a classical data, and we can input this classical data into the phase of the any rotational gate. There is so many three types of rotational gate exist in quantum computer. This is Rx, Pauli X rotation, Pauli Y rotation, and Pauli Z rotation. So by using this rotational gate within their phase, you can encode the classical data. Here, qubit requirement is same number of qubit is required as you have features in the your feature set. So uh, it's not required number of qubit as like as basis encoding, but it's required higher number of qubit in terms of amplitude encoding. But implementation is very easy in terms of NIST quantum computer. We have required only simple 1 qubit gates. This is Rx, Ry, or Rz kind of rotation gate. And if you want to make the more higher order in angle, then we have required number of more layers. Suppose we have a single layer of Rx rotation, then if you need a more complex or higher order angle encoding, then you can add extra more layer of this Rx rotation or Ry rotation or mixing of Rx Ry rotation. This is up to you as per your requirement. So in terms of implementation in this angle encoding is very simple, but still there is a limitation if you have a more than 200 features the more than 100 features in your feature set. Nowadays, computer only gives you the 156, 157 number of qubits. So within this limitation is still exists. But in terms of implementation, it is still easier than the amplitude encoding. And so we can say angle encoding is a Nixera encoding technique. So this is the very preliminary concept of the quantum machine learning. And next, this is the structure of. I'm going very. I want to go very first. This structure of quantum machine learning, because Professor Amlan Chakravarti already told you this structure. I have already told you the first task is you have to input the data by using the different encoding technique as per your need. You can do basis, amplitude, or angle encoding. Then you have required one variational circuit. This is called a PQ circuit. uh, this is the parameterized circuit and also entanglement of required. And from this one is a sample structure. This entanglement maybe you can use as per your requirement. There may be a linear arrangement of this entanglement or any or full entanglement. You can use this for variational. And uh, and state of this after encoding data, we can start with some basis parameter of this initial parameter of this circuit. Then we do some measurement. After this measurement, it goes to the your cost function and optimizer. Then updated parameter also again feed with this quantum circuit, and that means encoding circuit. Then again it will execute. This is the loop for quantum machine learning problem. And here I have used one thing. This is parameter shift rule. You know, this quantum circuit means this is a unitary matrix actually in form of mathematics. So making the gradient or derivatives of this unitary matrix is impossible. So getting the gradient of this unitary circuit, we actually in community research, they use a parameter shift rule. Here, suppose here what is happening for this circuit, if there is a 8 parameter, so for a particular one parameter, we fix this parameter and we add some extra shifting value with this, and all others parameter will be the fixed, and we will perform this quantum circuit operation. And also similar, we fix all 7 parameter and change the one parameter with this theta minus s. We, after computing this, we will find the what will be the next parameter. In this way, we find the gradient of this unitary matrix. This is called parameter shift rule. And within this structure, one is the basic problem of this quantum computer, quantum computing circuit. This is variational circuit. If you have a more entanglement, your expressibility becomes very high. For dataset expressibility will be the very high for this entanglement based PQC circuit. But there is a problem. There may be a chance of this can be stuck into the barren plateau because energy landscapes will change due to the high entanglement structure. So there is a highly chance. So beware of this barren plateau because for making the higher expressibility you can use for your circuit, the higher entanglement you can use, but it may give you the pain for the barren plateau. So this one is also another research for area of the quantum machine learning, how to avoid this barren plateau in high entanglement quantum circuit. Okay, this one is the basic preliminary. Now we are coming to the our research area. This one is Kolmogorov Arnold representation basis of quantum machine learning algorithm. We want to do this. So what is Kolmogorov Arnold representation? Actually, in Kolmogorov-Arnold representation, theoretically it says that if you have a multivariate function, you can learn this multivariate function as a superposition of several single univariate or a single variable continuous function as a superposition of. Here, this f is your multivariate function, and this can be expressed as a linear superposition of some univariate function. This is called an inner function. This phi qp is the inner function for individual features. This one xp is the individual features. You can write a superposition or sum of this mm, single variable function. And after doing this, there we have required a one outer function, and sum of this all outer function give you the can approximate this your multivariate function. This is the basic principle of Kolmogorov-Arnold representation. And by using this representation, there is a Kolmogorov-Arnold networks. What is this? This phi 1, phi 2, phi 3, they are the inner function. They can execute uh, uh, with a one feature set. Here is one basic difference between the Kolmogorov-Arnold network with a normal or neural networks. In case of neural networks, what is happened? Your features is there, and within the edge of this neural network, weight is coming, and intermediate nodes, it's a weighted sum is happening, and we learns this weight function, weight. But in Kolmogorov-Arnold representation, uh, this activation function, or you can say this univariate function, is come from the edge of this network. So univariate function, or we can, and in case of classical not a classical, any neural network, here activation function is predefined, and our learning parameter is weight. But in case of Kolmogorov-Arnold network, activation function, that means every inner function, or we can say every univariate function is coming through the edge, and they are the learning function. We actually learn individual features within this inner function. And then all of this function is weighted sum comes into the next layer of this node. This is the structure of Kolmogorov-Arnold network, and this is different from the normal neural networks. And uh, next statements may be a very debatable statement. Still, it is in research constant because they have said that some Kolmogorov unknown networks can outperform or more than efficient the convolution neural networks. But still, it is a debatable comments. We can do debate more than 1 and 2 hours within this comment. So ignore this comment. Still, we this is under in research. In case of classical Kolmogorov unknown network too, someone says that Kolmogorov unknown networks can perform better than the convolution neural network, but this is not true for all cases, and still it is in under research domain. So, in case of quantum Kolmogorov unknown network, before our paper, there is only one paper. This is from the Peter and Ivaskov group. They actually proposed this quantum version of this Kolmogorov unknown networks, and their idea is like block encoding based technique idea, and this is not a Nix friendly idea. Their idea is complete a fault tolerant based computing idea, and their graphical representation of their proposed quantum Kolmogorov unknown networks is like that. They use diagonal block encoding based technique for encode the data. I have already told you the amplitude encoding, basis encoding, and also the angle encoding technique. Technique for encoding. This is diagonal block encoding technique we are saying, but you can say that this one is a sub problem statement of sub kind of this amplitude encoding technique. It is another sub technique of amplitude encoding because here features comes into the diagonal matrix as a diagonal matrix, so it's required less number of less number of 1 to qubit gates to encode this by using this technique, diagonal block encoding technique. Then their network exists like this 511, 512, these all are the inner univariate function. As I told you, that by definition, we want to learn a multivariate function by using the some univariate superposition of univariate function. This univariate function or inner function is this 5152. They are coming from the edge, and after that there is a weighted average in the next layer of this network. And there is one question is coming: what will be the form of this inner function? Each and individual inner function should be a some function. What will be? So their paper they use the Chebyshev polynomial, and also in our paper we also use this Chebyshev polynomial technique for encoding the or for represent the inner functions. Sum of Chebyshev polynomial. This is the form of Chebyshev polynomial and weightage Chebyshev polynomial used for this each and individual inner function. And this is the actual outcomes. They have a block encoded outcomes. This one, see that this is P1. This is actually sum of all inner function. As we know, the what is actually required in our Kolmogorov representation, we require the superposition of inner function. So from their network representation, it is also still required this kind of, this one is representing the superposition of inner function. And if you design the number of layer, there is the each and every layer's outcomes. But if in terms of resource estimation, they have required first of all, a number of in terms of qubit, they have required a huge number of qubit because they use a block encoding based technique for encode the data set, which is a subspace of amplitude encoding. So if there is a L number of layer, then they have required the only ancilla qubit requirement is like this form. So it's a very costly process, and this is not possible to implement in our nowadays Niskera computing. So from this idea, we try to make our proposal that how can we implement in Niskera quantum computing. This and that's why we are saying that our technique is approximate hybrid quantum classical Kolmogorov Arnold network, because we want to use variational principal parameter circuit, and also our data representation by using this our architecture is a quantum, and we also use one single layer of neural networks. This is the our structure, and this structure also possible to implement in Niskera. We are, as I told you, that for representing this inner function, we also use Chebyshev polynomial for representing it. And this one is also challenging. How can we implement this Chebyshev polynomial in a quantum circuit? This is the main challenge in our Kolmogorov-Arnold network. So, same things, I'm not explaining this. So, same case in our case also, inner function is a weighted Chebyshev polynomial and a weighted sum. Now, there is a one question is that uh, for approximating the any univariate function, if we use a higher degree of Chebyshev polynomial, sum of this Chebyshev polynomial, then we can very accurately approximate the any univariate function. If D is very high, then if D is 9, that means we have required 9 individual Chebyshev polynomial sum. We have to make this quantum circuit, but this is also will be very difficult. So in this case, we have used a different tricks to reduce the quantum circuit depth. So here, uh, before giving to this answer of this question, I want to just explain what is this Chebyshev polynomial. Chebyshev polynomial is can if your x is the within this range of -1 to 1, then you can represent any Chebyshev polynomial Tn of x as a cos of n theta. This is very simple form, and some so T0 of x first one polynomial should be a constant, then T1 of x is a x1 polynomial, and this is the recurrence of this. And obviously there is a orthogonality exists on this Chebyshev polynomial, and also is extrema and roots is very known and very good in properties. That's why we use Chebyshev, and also its convergence rate is very high. That's why we use Chebyshev polynomial. So first, a few terms of this Chebyshev polynomial is like that. There is terms, and see, we want to encode our inner function as a sum of this Chebyshev polynomial. That means if we take a degree D as a 5, then sum of this T0 to T4, we need to make a quantum circuit of this. So sum of this Chebyshev polynomial is look like this. Here this first T0 terms, this one is x is T1 terms, this one is our T2, this one T3, and this one is T4 terms. And see, this can express as a sum of all the 4 terms. But can you cheat? This one is this your summation of all 5 terms give you this polynomial, and highest degree of this polynomial is 4, and there exist 4, 2, and 3 all this polynomial order. Uh, See, there is also very interesting thing. If we do sum of this only T3 and T4, then also we can get all the polynomial terms like x4, x3, etc. We don't need to add all of this T0, T1, and T2, because after doing some summation, we'll get only these terms. So, if we add only T3 and T4, then it is sufficient, not require T0 to 1. Obviously, coefficient will be the changes, but coefficient for learning one function, coefficient sometimes doesn't matter. And we also prove this in our paper. Detailed proofs I didn't give here. Just one line I said that this is possible to prove that. by using just only leading two terms. If we add, then it is sufficient for the getting the approximate the whole sum of this Chebyshev polynomial. This one is the one trick for reducing the circuit depth in our architecture. So there is another form of the if Chebyshev polynomial terms. This one is here says, and if your x value is within the range of 0, 1, x is our features. We can before going to the machine learning model, we can scaling our features between 0 and 1. So very easily we can write each and every Chebyshev polynomial terms as like this expression. I'm not explaining this. So I have told you last, really do we need, the question is, do we need the all the Chebyshev sum, Chebyshev terms to sum, getting the sum of weighted sum of this? No, we have required only leading to degree. That means if you choose the degree D, then only leading two terms, sum of these two terms like a D and D minus 1 polynomial. If you do this sum, then you can same way approximate the univariate function. And this is done by using this proof. We have fx is your all the sum of this unitary, and we drop the leading two terms. Still, it will be it will and its norms is not a larger than this. Details proofs is exist in our paper. I'm not going to explain this. So this is, we have done our first challenge. How can we encode our inner function by using the Chebyshev polynomial, and how can we reduce the circuit depth by taking only the leading two terms? We have solved this. But there is another challenge. This is outer function. What will be the outer function? Here we use outer function. This one. So we have done this, but sorry. So what will be the outer function? I'm really sorry for subting this slide. Actually, for the outer function, we have used a measurement operator as an outer function, because after measurement, we are giving a one classical neural network as a this measurement outcome will be the input for the one single layer of classical neural network. That's why it is a hybrid model. So from our case, so some of this Chebyshev polynomial can be explained in this way. This is another form of writing. This one is two leading terms, leading degree, and D and D minus 1. So this one is the representation. Now question is, how can we implement this in a quantum hardware? Or quantum, not a quantum hardware, how can we make this circuit? This is a mathematical expression. From this mathematical expression, how can we make the quantum circuit? This one is the challenge. So making these quantum circuits, we have required of two types, these four ingredients, and we use LCU based circuit, linear combination of unitary circuits. Here we have required these four control target unitaries, and these are the four main ingredients to convert these mathematical expression to a quantum circuits. So still you can think, how can we do it? This is actually you have to do some mathematical operations, then you can transform. I will show you the very first these steps, and maybe it's going to the very boring part of this lecture of the next 3 to 4 slides. It's a completely mathematical expression. How can you convert this mathematical expression to a quantum circuit? So I'm going very first this part. So taking a very simple example, suppose you have a only two features problem. So represent these two features, you have required a single qubit, and in case of making the Chebyshev polynomial representation, you have we have required the extra 3 ancilla qubit for our purpose. So initial psi preparation is like that. We have a this qubit number, fourth qubit is our features qubit, and about 3 qubit acting as an ancilla qubit. So and we will show you the resource estimation, how many number of ancilla qubit required in terms of if we have a n number of features. Before going to that, I just explain you the very simple case. How can you? So initially, and then we apply the Hadamard operation of individual qubit number 1, 2, and 3. And I think all of you know, if we do Hadamard operation, what will be this? So this one is the after doing this Hadamard operation. Next is fourth qubit. We have applied the RY rotation, and this is a parametric rotation. So alpha is our parameterized gate. So after doing this, we will get the next site, which looks like this. And after this, some simplified, we'll get this operation. There is 0001. Oh, sorry, there is one mistake. 10 of cos alpha 0 and alpha. This is missing. My mistake to making the slide. So there is 0001, 10, and 11 terms is coming from this Hadamard, and this cos alpha 0 cos alpha is coming from the RY rotation. Then we apply the our control unitary, and here U1 is designed in such a way, if our 2 and 3 qubit is 00, then U1 will acting this U1 target unitary will be acting on the qubit number 4. Similarly, if state is 01, then U2 will act, because it's a control. I think all of you know the Toffoli gate composition. If 2 qubit is 1, then target will be the flip. Similar, like here we also apply. I know this part is very boring, but I try to show how can you implement from the mathematical terms to a quantum circuit terms. So we apply this, and after doing this application, we'll get this formation. Here, you know, in the unitary, what is that? This e to the power, see that this is the target unitary. In target unitary, this theta 1, theta 2 is our features set. And why it is we have required 4? Because actually making the sum of this leading two terms, we have degree d and degree d minus 1. And see, for this sum of representing the degree d polynomial, we have two terms, e to the I theta 3 and e to the minus I theta 3. And for the previous next leading polynomial terms representing, we have required another 2 e to the y term. So that's why we have required a 4 unitary instead of any features. But size of this unitary obviously depending on the number of features. Here we are, for this example case, we are taking 2 features. That's why size of this unitary is 8 cross 8 matrix, because it's a 3 qubit gate. That's why. And see that target unitary is, this part is actually showing you the leading terms, and another part is the just previous unit. So after applying this unitary, we are getting this psi 3. And this theta 1 and theta 2 all are coming from the features, and these features is encoded into our unitary matrix. So this control unitary matrix. So it is automatically coming to the our site state. Next, we so just replacing this part, we can get the simplified form of this. Then we apply the Hadamard operation of over this one first qubit, and if we do, then we get this form. This is a simple. Don't I know this mathematical expression showing in slides is boring, but I try to very little idea how can we make this. So again, after doing the Hadamard operation over this, we'll get this expression. I'm not explaining, just step by step. So after doing this measurement of the first qubit, first 2 qubit, qubit number 1, not first qubit, sorry, first 3 ancilla qubit. We have a 3 ancilla and 1 features vector qubit. So we apply the measurement only the ancilla qubit, not the features qubit. So after doing this, we'll get these terms. What is that meaning of this term? If we put all the sigma value equivalent, then see, after doing something, we are getting these terms. This is actually your weighted sum of the Chebyshev polynomial for here our features 2. This one is x1 and x2 feature. This one, this theta 1 e to the power I in theta 1 minus This one is the leading terms of the first polynomial of the first features. That means first inner function. And this one is the leading polynomial of second features and second inner function. And this one is your just previous degree polynomial of the first features, and this one is similarly for the second feature. So this one is a polynomial, Chebyshev polynomial. So we can very easily write t1 x1, tn x2. Here tn minus 1 x1 is also missing by my bad for taking this slide, and tn minus 1 x is also there. So in this way, by using this quantum circuit, we can express this mathematical expression. And I will not show any more mathematical expression. Ignore this part, this one. So now in terms of resource, so if you have a n number of features vectors, feature size, then you have required features vector number of qubits is log 2n number of log n2 number of qubits is required for encoding the features vector. And for encoding the ancilla, not we have required ancilla qubit or supporting qubit. This is log 2n plus 1 number of this. Uh, this one is less number of ancilla qubit is required than the this Peter's propose Kolmogorov unknown network. We reduce the number of qubit requirements in logarithmic scale. This is the ancilla qubit, and this one for actual qubit. So this one is our circuit template, generalized circuit template. I have told you this one is our ancilla register. This one is our actual register. From this mathematical expression to circuit expression, you heard some name this Hadamard operation. We have to apply this. We have applied. This one is the Hadamard, and we have applied some rotational gate over the features vector as per this. This one is this, and this part is our weighted Chebyshev polynomial sum is coming within this part. This YOLO block encode block diagonal unitary, and this is the control unit. This one is a high level quantum circuit architecture. And number of 2 qubit requirement, because we claim that we want to implement in the next era. So we have required the 2 qubit number of gate is like that. If you have a 2 features, then 24. Still, it is a exponential growth of number of 2 qubit gate. But we within this talk or within this presentation, I will not show this future technique. Future, we have also got another technique reduce this exponential growth of this 2 qubits. That will come in our next paper. This is still not published. That's why I will not show in this lecture. So still here we have required an exponential number of 2 qubit gate requirement to implement this, but for the some limitation of this feature, still it is implementable in the next era. This is the complete pipeline architecture. This one is the features input. Then this one is the quantum block. What is this? This part actually comes into this block, and after this measurement we get some outcomes, and this act as a and our input of the classical one layer classical neural network. There is a activation function. If this for example purpose I am mentioning this soft function softmax, but anything can be here, and in this way it's work quantum classical hybrid. And application of the QCon, still we are not we didn't apply it for the very high or demanding data set. Just for the toy example, we try to from the at the starting of this session, I already told you that for our case this one is still under in the research domain. We are doing research, still it's going on. So our result here we are showing for the some toy example. This is no claim of beat the classical neural network. There is no claim of they outperform the others technique. We are not claiming anything like this. We try to just characterization this model. But if we implement the quantum colmograph neural networks in Niskera, what will be the characterization of this model? uh, which type of data it can handle. So this research is still going on. So I will show the some very simple result or some toy example. One is we have using the iris data model, and we have got the 96% accuracy for the multi-class classification for this iris in by using this quantum machine learning model. And we also try to see that our model is capable to handle the non-linear data set. That's why we try to some synthetic data sets like Swiss roll and also spiral data set. We try to implement, try to check this. Uh, just to very first, I will show this. This is the some performance metrics of ID's data set, and this is our uh, training versus validation loss result set and validation for ID. And we also working on the try to check this what's the performance for this nonlinear data set. This is Swiss roll data set. This is the synthetic generate of data set. And we also use some noise, introduce some noise within this data set and try to check this for a single layer QCon approximate Kolmogorov hybrid networks can work or not, and what will be the performance. We are not claiming that we are getting very good result or anything. So this one is a result we are getting for the Swiss roll, and I'm not going. And also we have done checking our model with this spiral data set also, and with some noise and with a very less number of noiseless, we are getting this kind of result. And this is performance metrics of this result set. And future plan, actually, we try to implement for a big data set like fashion MNSIT and Cipher 10 data set in real quantum hardware by using our Kolmogorov hardware. This task is going on in IBM hardware. Still, we are not getting result. We try to perform, make our modeling good. And also, we have got one project from the NVIDIA. This one is we try to check our model's performance of Alzheimer's dataset, and this task is also going on. And another things, in case of our quantum machine neural network model, uh, suppose our feature set is very high, then available number of qubit is mostly one maximum 1.57 number of qubit. Can we cut this circuit quantum neural network circuit to distribute in the different machine to and then collect this result and make a machine learning model? This is we check. This is nearly impossible because quantum neural network there is their circuit model or PQ circuit is very highly entangled based circuit. So circuit cutting is very costly for their case, and also cutting is not, you can say cutting is not costly, but reconstruction will be the very costly. But there is a one advantage of our model. We can make a distributed mixture because due to this inner function, see, this inner function is a superposition sum of this. So very easily we can distribute some. Suppose we have a six, say 1,240 kind of features inside. We can break it to for 10, 10, 10 number, and for this 10 we can, because this is a linear superposition as per the demand of Kolmogorov sir. So summation but we can cut and we can execute in a different quantum machine, like we can execute in a IBM's one quantum machine. This can be another quantum machine. Parallelly we can execute this, and we have tested this model uh, in real hardware. It's possible. and hopefully this result will come in our next paper. And also federated learning setups, we try to develop our model into federated learning setup. Still, we are not getting any result for the federated learning setup, but we assume that it is possible by using quantum computer in the federated learning setup. We are working, and this is our collaborator of this. Here, Dr. Shian Samanday Chaudhary is in also a member of our TCG press team. And there is Turbushu. He is a doctoral research scholar of North Carolina University. Arnav is an external member of, he is working on one company. And all of you know the Professor Amlan Chakraborty, and also he is a professor of Calcutta University, A.K. Chaudhary, director of A.K. Chaudhary School of IT. And also there is a Professor Sabri Kais is one of the collaborators. He is professor of North Carolina University. That's all. Thank you for listening.
And from the participant, any queries? Dear participants, do you have any queries regarding this session? Nobody is asking any question.
Okay, might be it's a last session. And everyone is tired after Ritoji's and Novi's.
No, I think someone.
Okay, someone I think in chat box. I think, yeah.
The chat box, somebody's written something. Yes, yes.
Sir, how to know which? First of all, don't call me a sir. I'm a quantum engineer. I'm not a sir. So, how to know which circuit will perform best or be random? No, there is no random process for choosing the quantum circuit. And see, first of all, you have to check the expressibility of your circuit. There is a some technique before going to this. You can check the expressibility of your quantum circuit or quantum representation. Like you can if you use a less number of by intuitively you can check this. If you have a less number of entangled state in your PQC circuit, then it's a less expressible, but there is a less chance of barren plateau issues. So uh, there are so many technique like this. You can check the Haar measurement. There is a quantum from the quantum information technique. By using Haar measurement, you can check the expressibility of your unitary circuits, and also you can check the expressibility by using your validation data set and try to find the Wasserstein distance kind of algorithm you can use to check expressibility of your circuit. So there is not a fully random, but there is a some intuitive base. There is no perfect thumb rules. Okay, for this you can use this circuit. For this you can do this circuit. There is no thumb rule, but not a random guess. There is some intuitive base and some measurement things like a hard measurement, and also you can do the Wasserstein distance between these two quantum circuit with your validation and your test set.
So, thank you, sir, for this wonderful session. It is very insightful. And you have shared your PPT also. We will share the PPT to the participant. And if anybody ask any question regarding your presentation, then we will definitely inform you through email.
Yeah, definitely.
So the technical session is now completed. We have some information for the participant. Dear participant, we are now at the final online test and feedback portion of the FDP. There is a time slot, and within that time slot, you please complete your feedback and online test through your ATAL portal login. If you face any problem, then write in WhatsApp group. We will look into this. We have submitted the attendance. We are going to submit the attendance, and online test will be probably activate from 6:45. And after submitting your feedback and online test, you will get the certificate from ATAL portal. After that, the validation session will be started from 7:30, around 7:30. I will send the link, and in the link, the time will be mentioned. The participants are requested to attend the valedictory session positively. In that session, we will take the feedback of some participants, and that feedback will be uploaded in the YouTube also. So you will give your feedback online once in the ATAL portal, and another online feedback we will take through your mic and video in the valedictory session. So with this information, we will now close the technical session, and then we will meet soon after your exam and feedback submission. Okay? Any queries from any participant? So with this information, we are now closing technical session 13. Next, we will meet at the valedictory session. The link will be provided soon. Thank you very much.